have you ever, stopped to really think about that invisible force? The one buzzing through your walls right now, powering everything. Your lights, your phone charging, keeping the fridge cold.
Yeah, it's everywhere.
It's this constant dynamic dance, really. And understanding the choreography of that dance, well, that's kind of key to everything in our modern lives.
Absolutely.
So today, we're diving deep into the fundamentals of alternating current AC, that invisible engine driving so much of our world. Our sources for this deep dive, they're a set of really practical instructional materials, the kind of stuff aspiring electricians study.
Right, the foundational knowledge.
Exactly. And we're going to use them to give you a bit of a shortcut. Yeah. To being genuinely well-informed about AC.
That's the plan. Our mission is to take these detailed sources and pull out the clearest, most impactful bits for you.
The nuggets.
The nuggets, yeah. We want to unpack how AC is actually generated, what dictates its rhythm, its frequency, and critically, how we measure its different values. Because it's always changing, right? Constantly.
So how do we measure it consistently? It's about cutting through that complexity to get to the elegant simplicity underneath it all.
So whether you're just, curious about the power flowing in your home, or maybe you're looking to get a serious head start on understanding electrical theory, you're going to walk away with some crucial insights, really understanding what makes modern electricity tick.
Definitely.
Okay, so let's unpack this. What's the absolute, secret sauce? What gets electricity moving in the first place? How does this whole show even begin?
Yeah, it all boils down to a really fundamental principle. It's called relative motion.
Relative motion.
Yeah. Just imagine a conductor, usually, a wire in a magnetic field. For electricity to happen, one has to move in relation to the other.
Okay.
So you can either have the conductor moving through a stationary magnetic field,
Right.
or you can have the magnetic field sweeping past a stationary conductor. Either way works.
And when that dance, that relative motion happens, something called an electromotive force, or EMF, gets developed in that conductor.
EMF, and that's what we usually call
It's voltage. We commonly know it as voltage. It's the electrical pressure, essentially.
Got it. So we're basically taking mechanical movement and turning it into electrical potential. But is the amount of voltage always the same, or are there specific things that, crank it up or down?
That's a great question. Because, no, it's definitely not fixed. There are three critical factors that influence how much EMF, how much voltage you generate.
Okay, 3 factors.
Yep. First, there's the density of the magnetic flux.
Flux density sounds technical.
It just means how many magnetic lines of force are packed into a certain area. Think of it as how strong the magnet is, basically. More lines, more potential for cutting, more EMF.
Makes sense. More lines to cut. What's second?
Second is the length of the conductor that's actually doing the cutting within that magnetic field.
So not the total length of the wire, just the part interacting.
Exactly. The longer the segment interacting with the field, the more EMF you get.
Okay. And the third, you said this one was important for AC.
Yeah, and this is crucial for AC. It's the rate at which the conductor cuts those magnetic lines of force.
The rate. So how fast it's cutting?
Well, yes, speed matters, but it's also about the angle it's moving through the field. That's really key.
The angle. Okay, that sounds like where the real magic happens for AC, doesn't it?
Right.
Because I'm picturing this, if you just slide a wire, parallel to the magnetic lines, nothing much happens, does it?
Precisely. If a conductor moves perfectly parallel to those lines, it's just sort of gliding alongside them. It's not actually cutting them. And because there's no cutting, no EMF is generated. Zero voltage.
But if you slice across them,
like
at a right angle.
Now you're talking. If you move that same conductor, same speed, but make it slice directly across those lines, a perfect 90-degree angle, that's when you hit the maximum possible EMF.
Maximum voltage at 90 degrees.
Yep. Think of it like a boat crossing a river. If it goes straight across, it fights the current most directly, right?
Yeah.
But if it just drifts downstream, parallel to the current, it's barely interacting. Same idea here.
That's a great analogy. Okay. So if we imagine a conductor spinning, in a circle through a magnetic field, kind of like what happens in a generator.
Exactly like in a generator.
Even if its spinning speed is constant, the angle it's cutting those magnetic lines at is changing all the time.
Constantly changing.
And that continuous change in angle means the voltage it generates is also continuously changing. This is it, isn't it? This is where the sine wave comes from.
Absolutely. That is the aha moment for alternating current. As that conductor rotates, let's say starting at 0 degrees,
Okay.
it begins cutting lines. At 90 degrees, boom, It's cutting at the maximum rate, maximum angle, so you get maximum positive EMF,
The peak.
the positive peak.
Yeah.
Then, as it keeps spinning, the cutting angle decreases. Less and less cutting. Until at 180 degrees, it's moving parallel again, momentarily.
Back to zero EMF.
Back to zero. But then it keeps going. Now it starts cutting lines in the opposite direction relative to the field.
The other way.
Right. Building up EMF again, but this time it's negative voltage, reaching maximum negative EMF at 270 degrees.
Negative peak.
Exactly, before finally returning to the starting point, 360 degrees, back at zero EMF.
So you've got 2 points of maximum voltage, 90 and 270, and 2 points of zero voltage, 0 and 180.
That's the pattern.
And this whole rotation, this entire elegant sweep from 0 up to max positive, back to 0, down to max negative, and back to 0 again. That whole thing is what we call one electrical cycle. It's like a complete breath in and out.
Exactly, a perfect description. When a conductor loop in a generator rotates past one pair of magnetic poles, one north pole and one south pole, it completes one full electrical cycle.
One cycle per pair of pills.
Per rotation, yes. And this cycle, it's actually made up of two distinct halves called alternations.
Okay.
You have the positive alternation from 0 to 180 degrees where the voltage pushes current one way. And then you have the negative alternation from 180 to 360 degrees where the voltage reverses direction, pushing current the other way.
It reverses. That's the key.
That reversal is everything. Because the direction of motion through the magnetic field changes relative to the poles, it flips the polarity of the induced voltage. And that makes the current flow back and forth.
Alternating.
Alternating. That constant flip-flopping back and forth is precisely why we call it alternating current.
Wow. Okay, so if you were to actually graph all those instantaneous voltage values over time, you'd literally draw that classic wavy line, the sine wave.
You got it. That's the visual signature of AC, this continuous rise, fall, and reversal.
But this brings up a really important question for me. If it's always changing, always moving up and down, how do we ever talk about its speed? Or, measure it consistently?
That is the perfect segue, because once we understand how this dance is created, we absolutely need to talk about how fast it's dancing.
But the rhythm.
The rhythm, exactly. And like you just said, one complete sine wave equals one electrical cycle.
And the machines that do this for us, the ones giving us usable electricity, those are the AC generators, right? Or alternators, I think you called them.
Yep, alternators is the common term. They're essentially these big machines with conductor coils spinning inside powerful magnetic fields. Or sometimes the field spins around the coils.
Okay, so the speed. How fast is this happening?
That speed is called the frequency. It's defined really simply. The number of those electrical cycles completed in 1 second.
Cycles per second.
Exactly. We use the symbol F for frequency, and the unit is the hertz, abbreviated hertz. You might still hear the older term cycles per second sometimes. 60 cycles per second is just 60 hertz.
Okay, 60 hertz. I hear that a lot for North America.
That's the standard here, yes.
Yeah.
And just quickly, the flip side of frequency is the period. That's just the time it takes to complete one single cycle.
Got it. So frequency is cycles per second, period is seconds per cycle. Now, what's really fascinating, you mentioned this earlier, is how the actual design of the alternator, specifically its magnetic poles, affects the frequency. I kind of just assumed it was all about how fast you spin it.
Speed is definitely part of it, but the number of poles is equally crucial. Think about it simply. If an alternator has just one pair of magnetic poles, one north, one south, then for every single full mechanical rotation of its shaft, that's 360 mechanical degrees, it completes exactly one electrical cycle. 360 mechanical degrees equals 360 electrical degrees. Simple.
Okay, one rotation, one cycle.
But here's the clever engineering part. If a generator has multiple pairs of poles,
more magnets.
right, it completes more than one electrical cycle for each single mechanical rotation.
Wait, hang on. So like a machine with 4 poles, that's 2 pairs, right? North-south, north-south?
Exactly, 2 pairs.
It would generate 2 cycles for every one spin.
You got it. A 4-pole machine produces 2 full electrical cycles. That's 720 electrical degrees for every 360-degree mechanical turn.
Wow. And an 8-pole machine, that's 4 pairs, would do 4 cycles per spin.
Precisely. The more pole pairs you pack in, the more electrical cycles you squeeze out of the same mechanical rotation speed. It's like having more bumps on a wheel hitting something each time it turns.
That's a neat way to think about it.
Yeah.
So what does this all mean for, the power grid? Why is this important?
It means the output frequency of any AC generator, the Hertz value, is ultimately set by just two key things.
Okay.
One, the total number of individual poles in the machine, and two, the rotational speed of the generator shaft, which we usually measure in revolutions per minute, or Raman.
Poles and speed. Change either one, and you change the frequency.
That's the relationship.
Is there like a formula for that?
There is, and it's really important for anyone working with this stuff. The formula is FPM 120.
Okay, FPN 120. Let's break that down. F is frequency in hertz.
Correct. P is the total number of individual poles, not pairs, the total count.
Gotcha. So for a 4-pole machine, P is 4.
Right, and N is the rotational speed in revolutions per minute, Truman.
Okay. And what's the 120 doing on the bottom?
Ah, the 120. It's basically a conversion factor rolled into one. It accounts for converting poles to pole pairs, dividing by 2, and converting revolutions per minute to cycles per second, dividing by 60. 2 times 60 gives you 120. It just makes the math cleaner to get hertz directly.
Clever. Okay, let's try that example from our sources. Make it real.
Yeah, let's do it. Say we have an alternator with 4 poles, so P equals 4.
Okay.
And it's spinning at 1,800 revolutions per minute, so N 1,800.
Right.
Plug it in, F equals 4, 1,800, 120.
Okay, 4 times 1,800 is 7,200. Divide that by 120.
And you get 60.
60 hertz.
Exactly. The standard frequency right here in North America,
Yeah.
that combination of poles and speed is extremely common for power generation.
So the big takeaway here is,
Yeah.
do you want a higher frequency? Either spin the generator faster or design it with more poles.
That's the fundamental relationship. It's a really neat piece of engineering.
Okay, this is great. We've gone from how AC is born, understood its rhythm, its frequency. But now let's tackle the next big puzzle. How do we actually talk about the strength or the value of the voltage and current? My wall plug says 120 volts. But we just established the voltage is always changing, rising, falling, even reversing. So what does the 120 volts even mean? Why not just tell me the peak voltage it hits?
That is precisely the question, and it's why we need different ways to define the value of AC. The first one is that peak value you mentioned. We call it the maximum or peak value, usually written as Emax or Vmax or sometimes E-peak.
And that's just...
That's simply the highest point the voltage or current reaches during an alternation. As we discussed, for a nice clean sine wave, those peaks happen at 90 degrees positive and 270 degrees negative.
Right, the highest and lowest points.
Exactly. You might also sometimes hear about peak-to-peak voltage, which is just the total voltage swing from the positive peak all the way down to the negative peak.
Okay, peak value, got it. What else? You mentioned instantaneous values earlier.
Right, instantaneous values. Think of these like taking a snapshot.
A single moment in time.
Precisely. They're usually shown with a lowercase letter, like E for instantaneous voltage or E for instantaneous current.
Right.
This is literally the value, the voltage or current at any specific instant or angle within that cycle, and it's constantly changing moment to moment.
Is there a way to calculate that?
There is. For a sine wave, our sources give a pretty straightforward formula. E-E-E-S EMX angle.
Okay, instantaneous voltage E equals the maximum voltage Emax times the sine of the angle at that moment.
You got it. So quick example. If your maximum voltage, Emax, is, say, 10 volts, the instantaneous voltage, EO, when you're 20 degrees into the cycle would be 10 V sin, 20 degrees. Sine of 20 degrees is about 0.342. So the voltage at that exact instant is roughly 3.42 volts.
Okay, so it depends entirely on where you are in the cycle.
Entirely. It's a constantly moving target.
All right, so we have the absolute peak, the highest point, and we have the snapshot value at any given moment. But connecting back to my 120V wall outlet,
Correct.
What is that 120V? It's not the peak, and it's not just one instant. What's the practical everyday number we actually use?
Now we get to the most important one for practical purposes. This is the effective value. It's also universally known as the RMS value.
RMS. I've definitely seen that. What does it stand for?
Root mean square. It's a mathematical way of finding a sort of average, but it's a very specific kind of average.
Okay. And why is this the important one?
Because the RMS value represents the equivalent heating effect. Here's the key. An AC circuit with a certain RMS voltage will produce the same amount of heat in a resistor as a DC circuit with that same voltage value.
Oh, okay, that's useful. So like a 100-volt RMS AC circuit heats up a light bulb filament just as much as a steady 100-volt DC circuit would.
Exactly the same heating effect, assuming the resistance is the same. That's the why behind RMS. It gives us a direct, practical comparison to the steady power delivery of DC. It tells you the AC's effective working value.
Okay. So when I see 120 volts or 240 volts labeled for household power, those are always the effective, the RMS values.
That's the standard, yes. Unless it specifically says peak or something else, you assume it's RMS.
And my multimeter, when I stick it in the wall socket on the AC setting, it's reading RMS.
Yep. Most standard AC voltmeters are calibrated to read the RMS value of a sine wave.
Okay, that makes sense now. And you mentioned for a pure sine wave, this RMS value happens at a specific point.
Mathematically, yes. For a pure sine wave, the instantaneous value equals the RMS value at 45 degrees into the cycle. Also at 135, 225, and 315 degrees.
45 degrees, got it. So understanding the conversion between the peak value and this effective RMS value must be pretty crucial then, for safety for equipment.
Absolutely essential. You need to know how to go back and forth. Let's make it really clear. If you know the RMS voltage, like your 120V outlet, and you want to figure out the peak or maximum voltage.
Yeah, how do we do that?
Okay, two main ways. You can take the RMS value and divide it by the sine of 45 degrees. Sine of 45 is about 0.707. So RMS 0.707.
Okay.
Or, maybe a bit easier for quick math, you can just multiply the RMS value by the square root of 2. Square root of 2 is about 1.414.
RMS times 1.414 gives you peak.
Exactly. So let's do your 1.4114. What's the peak voltage actually hitting your devices?
Okay, 120V times, let's use 1.414. It comes out to, wow, 169.68 volts, nearly 170 volts.
Right. That's a big difference from the 120V label. The voltage is actually peaking way up there, 60 times a second in each direction.
That's wild. Okay, so how do we go the other way? If we know the peak, how do we find the RMS, the effective value?
Just reverse the math. You can either multiply the peak maximum value by sine of 45 degrees, that 0.707 number.
Peak times 0.707.
Or you can divide the peak value by the square root of 2, that 1.414 number. Peak divided by 1.414.
Either way gets you the RMS value. So using your peak number, 169.7V, multiply that by 0.707.
169.7 times 0.707.
Yep, it comes right back to about 120 volts.
Perfect.
This is such a critical distinction then. Knowing this isn't just like academic trivia, it's vital for understanding what your appliances and electronics are really dealing with. Why components might need much higher voltage ratings than just the 120V number suggests.
Absolutely. It ensures that devices can safely handle those instantaneous peak voltages, not just the average heating effect represented by the RMS value. It's truly foundational knowledge for anyone working safely and effectively with electricity.
Wow. We have covered a fascinating amount of ground today.
Yeah.
Seriously. We traced the journey of AC right from its elegant mechanical birth.
The relative motion dance?
Yeah, that dance between conductors and magnetic fields. Then we explored the whole rhythm of a frequency, figuring out how poles and speeds set the pace. And finally, we kind of decoded the wave itself, learning the really crucial differences between peak, instantaneous, and that practical effective, or RMS, value. It's really a dance of physics and engineering working together.
It really is. And understanding these fundamentals, it genuinely demystifies that invisible electricity that powers, well, everything around us. It turns that sort of mysterious force into something comprehensible, predictable. It makes you a more informed consumer, definitely a sharper student if you're learning this stuff, or even helps you on the path to becoming an electrician. It just shows how precise engineering leads to the reliable power we pretty much take for granted, right?
Totally. And knowing now that your 120V wall outlet is actually zapping your devices with peaks of nearly 170 volts dozens of times every second, what new questions does that spark for you, about the gadgets you plug in every day? Or maybe even about the future of energy generation and storage, especially as we look at more dynamic power sources. It's a powerful thought, isn't it? Designed to electrify your curiosity,